Hi, and welcome back. It's Root Beer here. We're going to be finishing off the 2014 Friar contest. So that's the 9th grade level contest, and we're on to the last question, question number 4, so let's take a look. Okay, the set A, consisting of 2 and 1, has exactly 4 subsets. The set containing nothing, also known as the empty set. The set with just 1, the set with just 2, and A itself, which consists of 1 and 2. The 4 subset sums of A are 0, 1, 2, and 3. So there's nothing to add up here. 1, 2, and then 1 plus 2 is 3. The sum of the subset sums of A is 0 plus 1 plus 2 plus 3 equals 6. Note that, I already mentioned this is the empty set, and that 1, 2 is the same as 2, 1, so you can't get a different subset by reordering things. Alright, A part. The set 1, 2, 3 has exactly 8 subsets and therefore has 8 subset sums. List all 8 subset sums of 1, 2, and 3. Okay. Well, it might be helpful if we figured out the 8 subsets. So we have 1, 2, and 3, and we want the 8 subsets out of that. We have 8 subsets. We could have none of the elements in here, so we can just have the empty set. It's best when we're listing these sorts of things out to be methodical. So, how about we figure out everything that doesn't have a 1 in it. So that gives us 2, 3, and 2, 3. And now everything that does have a 1 in it, 1 all by himself, 1, 2, 1, 3, and lastly 1, 2, 3. So with these sorts of subsets, you can either have 1 in your subset or not. You can either have 2 in your subset or not. You can either have 3 in your subset or not. So there's always 2 choices. Is 1 in or not in the subset that we're talking about? And that's why 2 times 2 times 2, there's a total of 8 choices. That gives us our 8 subsets. So the empty set, that's our case where we have chosen that none of the numbers are in the subset. Here we've chosen 1 and 2 to be in the subset, but not 3. Here we've chosen them all to be in the subset. So that's just how we would sort of think about why we get 8 subsets here, and how we might methodically go about adding these subsets. Which subsets, list all the subsets that don't contain 1, and then all the ones that do contain 1. And of those subsets, list all the ones that don't contain 2, and then the ones that do contain 2. That sort of stuff. So here we get a subset sum of 0, 2, 3, 2 plus 3, which is 5, 1, we don't have anything to add up, 1 plus 2, so that's 3, and 1 plus 3 gives us 4, and finally 1 plus 2 plus 3 gives us a total of 6. So here are our 8 subset sums. And that's what we were asked to do. So we could list that in any order we wanted to. You might want to rearrange them to be in numerical order. Notice that we have 2 3s there. Okay, so list all 8 subset sums. Well, we did more. We actually listed out all our subsets and then figured out the subset sums. That was A. How about B? Determine, with justification, the sum of all the subset sums of 1, 2, 3, 4, 5, that set. Okay. So when figuring out the subset sum, we just add up all the numbers in the subset. So 1 can either be in the subset or not. 2 can either be in the subset or not. And that's the sort of thing we should have here. So we have 5 elements in the set. So we have two choices. Either one is in that subset or not. So in total, we get 32 subsets. Now each subset that contains 1, how many of those are there? Well, it could either contain 2 or 3 or 4 or 5, 2 choices for each of those. So when we're working out the sums of these subsets, 1 will be added in 16 of these sums, and then in the other 16 sums where 1 isn't in the subset, 1 won't appear. Okay. So if we want the sum of the subset sums, which let's just double check that's what we're asked for, the sum of all the subset sums, we don't need to work out each one of the subsets, or even each one of the subset sums. We just need to know how many times is 1 going to be added up, how many times is 2 going to be added up, and so on. We're going to be adding up 16 1s, 16 2s, all the way up to 16 5s. So if we wanted a fast way to figure out the total, we'd just do 16. So 16 1s, plus 16 2s, plus 16 3s, plus 16 4s, plus 16 5s. Okay? We don't know which subsets 1 appears in, but we know that 16 times he's going to appear in a subset. And so 16 times he'll be in a subset sum. Now, if we're going to add up all these sums, then we really just need to account for, there's going to be 16 1s in total. 16 1s contributing to the total value. Same with the 2s, same with the 3s. So 1 plus 2 plus 3 plus 4 plus 5, that's 15. And 16 times 15, you can work that out on your calculator or work it out by hand or in your head. We get 240. I use the word so a lot. So the sum of all subset sums is a nice 240. Okay. So a little bit of combinatorics there in terms of determining how many subsets 1 is in, how many subsets 2 is in, and that sort of stuff. But very basic combinatorics, so easily at a 9th grade level if you've seen that sort of stuff. And hopefully if you're doing these contests, you are aware of some basic combinatorics and counting principles. So C part. Determine, with justification again, the sum of all the subset sums. So once again, we're just going to be adding up all the subset sums. So we probably don't need to figure out each individual one. Of 1, 3, 4, 5, 7, 8, 12, 16 that are divisible by 4. So this divisible by 4 is adding a little bit of a wrinkle to it. Fortunately, this is the last question on the contest. Yep. So we can certainly, hopefully we've got a little bit of time banked up from doing the previous questions quickly. And we can fiddle around with this one a little bit. So we want subset sums that are divisible by 4. Okay. So we start on a brand new piece of paper, and just as I've been doing, let's write down the set. 1, 3, 4, 5, 7, 8, 12, and 16. Okay. So, we're going to have something like 1 plus 3 plus 4, for example. But picking out particular examples doesn't really help us right now. We could probably experiment a little bit by picking a bunch of examples. But, okay, so I notice I've got 4 numbers that are already divisible by 4. So I'm going to have 4 in one of my, the let's say, valid subset sums, the subset sum that is divisible by 4. 4 will be one of the terms there. It can only be one of the terms if the rest of the subset sum, so the rest of the numbers in the subset, other than 4, add up to be a multiple of 4. Okay. So each of these is divisible by 4, so they are islands unto themselves. They're self-contained. And we're left with 1, 3, 5, and 7. So when, if ever, are any of these in a subset sum? We can't have 1 by himself. We'd have to pair him up with something. Otherwise, we'd be congruent to 1 modulo 4. So if I have none of them and I have some 4s, 8s, 12s, 16, any of those, I'll get a sum that's divisible by 4. Now, if I want a 1, I need to pair them up with something. I can pair them up with 3 or 7. So if I have a 1, I can have 1 and 3. I can have 1 and 7. I can't just have 1 and 5 by itself. That would give us a sum of 6, and that would be no good. How about a 1, a 5, and something else? 1, a 5, and 3, that's 9. 1, a 5, and 7, that's 13. That's no good. How about 1, 3, 5, 7? So these are the possible other parts of our sum that we can have. Maybe it would be best not to write these as subsets, because that could get confusing. So if we have no 1, but we do have a 3, we have to have the pairing 3 and 5. 3 and 7 won't work, that's 10. 3, 5, and 7, that's odd, 15, so that's not going to work. So we have to have 3 plus 5 as part of our sum, and no 1. So we can't have 1 plus 3 plus 5 plus 7. That one's already counted for. So if we don't have a 1 or a 3, but we do have a 5, then we will have 5 plus 7 in our sum. And you can't just have a 7 by himself, just like you can't just have a 5 by itself, a 1 by itself, or a 3 by itself. So in addition to the multiples of 4, which come and go as they please, we can also have exactly 1 of 0, 1 plus 3, 1 plus 7, 1 plus 3 plus 5 plus 7, 3, 5, or 5 plus 7. Okay. So now, assuming that I had a 1 plus 3, what are the possible sums that I could have there? So there are So we have exactly 16 subset sums. Right, if we assume we have 1 plus 3 in our subset sum, then we can either have 4 or not. We can either have 8 or not. We can either have 12 or not. We can either have 16 or not as another term in the sum. So since 1 plus 3 is fixed, each of those other ones, the 4, the 8, the 12, the 16, would give us 2 choices. And that's 2 to the 4, so that's 16 choices. Okay. So we can jump straight to the sum of all subset sums. Right, we can either have 0 or not. We can either have the 1 plus 3 or not. We can either have the 1 plus 7 or not. These guys are all mutually exclusive. Times, and then 8 times 4 will appear in the sum. Exactly half the time, half of the 16 times 8 will appear in the sum. Exactly half the time 12 will appear in the sum. And exactly half the time 16 will appear in the sum. Okay, and we multiply that by, is 0 the rest of the sum? Is 1 plus 3 the rest of our subset sum? Is 1 plus 7 the rest of our subset sum? Is 1 plus 3 plus 5 plus 7 the rest of our subset sum? And so on. And that's why we multiply it by the sum of all those. Alright, well, if we work that out, we get 0 plus 1 plus 3 plus 1 plus 7 plus 1 plus 3 plus 5 plus 7 plus 3 plus 5 plus 5 plus 7. That gives us 48. Another way to see that is it's 3 times 1 plus 3 plus 5 plus 7, which is 3 times 16, so that's 48. 48 times 8 times 4 plus 8 is 12, plus 12 is 24, plus 16, that's 40. So 40 times 8 times 48. Is 15,360. And that should be The sum of our subsets, no. Is it? Yes, it should be. So the problem here is I've added these up, and I think that might be wrong. Because I've added these up, and 4 can either be in it or not. 8 can either be in it or not. 12 can either be in it or not. 16 can either be in it or not. But that's like saying 1 plus 3 can either be in it or not. 1 plus 7 can either be in it or not. And these are mutually exclusive. So I think I have done something wrong. Ah, okay. I have done something wrong. Half the time the 4, 8, so there's 8 possible. Half the time these guys appear. Sure. And how many of these cases are there? 1, 2, 3, 4, 5, 6. So 6 times 8 appearances of 4 or 8 or so overall, over all the total subset sums, there's 48 appearances of 4. There's 48 appearances of 8. But there's also 16 subsets with 0. 16 subsets with 1 plus 3. So 16 appearances of each of these guys. Okay, so I think that should be a little better. Let's see if that plays nicely with my intuition. See, I was originally skeptical because I was multiplying and I had a sum of things that could either be in or out, and then I had a sum of things that had to be in. And so that's why I was a little suspicious on second glance. So now, if it's 1 plus 3, that's going to appear 16 times. There's 16 subset sums with each of these. Okay, so that makes sense there. And then in those 16 subset sums with 1 plus 3, 4 will appear 8 times. 8 will appear 8 times. 12 will appear 8 times. 16 will appear 8 times. And that's not just for the 1 plus 3 case. We have 0, we have 1 plus 3, we have 1 plus 7, 1 plus 3 plus 5 plus 7, 3 plus 5, and 5 plus 7. So there's 6 different cases of what the odd numbers can be in our subset. And so for each of those 6 cases, 4 will appear 8 times. So that's why I think this number is a little better. I really hope this one's correct. So 6, so that's going to be 48 times 40 plus 16 times, what was it again? 1 plus 3 plus 5 plus 7 times 3, so that's going to be 48. So that's 48 times 56, which I can write a little better. Alright, 2688, that's a much lower number than the 15,000 I had originally. That's a little more believable, and I'm pretty sure this method is correct. Okay. So 2688, and we have explained where everything came from. Let's just recap a little bit. So we want sums that are divisible by 4. The 4, 8, 12, and 16, they can either be in or out. They're not going to affect divisibility by 4. What does affect divisibility by 4 are these odd numbers. And they have to either go in pairs or groups to give us sums of 4. So we can either have none of them, 0 is divisible by 4, or we're going to have 1, 3, 1, 7, 1, 3, 5, 7, 3, 5, and 5, 7. Those are the only ones we can have. So that's 6 possibilities. So if we fix one of these, if 1 plus 3 or 1 plus 7 is part of our term, then we can either have 4 or not. We can either have 8 as a part of the sum or not. 12 is part of the subset or not. 16 is part of the subset sum or not. And that gives us 16 different sums with a 1 plus 7. That's why 7 will appear, or 1 plus 7 will appear 16 times. Now, if of a fixed subset, either 4 appears in it or not. So 8 appears in it or not, 12 not, 16 either appears or not. And so half the time, if 4 appears, he's going to appear 2 times 2 times 2, which is 8, or half the time. So 8 times in one of any of the 6 situations, 4 will appear. So that definitely works, and we have explained our reasoning, our combinations, why when 4 appears, when it doesn't appear, and all in all, it gives us a sum of 2,688. So that should be our final answer. And as I said, C is the last part. We determined and we justified it. We explained our reasoning. We explained where divisibility by 4 came from. So overall, a nice question. I think it was about the equal of question number 3 in terms of difficulty. Both of them had different approaches. Obviously, one was a game theory question. One was sort of this subset sum, so it's a combinatorial question. But both of them were equally, I would say, challenging. Neither one was harder than the other. They're just different. And that's nice. I like it when question 4 is basically as hard as question 3, because sometimes question 4 can get really, really hard. But that concludes the 2014 Friar. So if you like the video, give a like. If you like the whole series, give it a like. And feel free to subscribe for more mathematics videos. It's been wonderful talking to you guys, and hope to see you guys in another video. So, Root Beer out.